Greetings, math people. Welcome back for another exciting journey through math land that we get to take together. Today we're beginning Unit 5. So we're actually skipping 5.1. Well, I shouldn't even say that because I might be using this on a year where I didn't skip 5.1. So just ignore that part. I'm trying to make these videos as universal as I can. I'm making them during the COVID years. You might be watching this video some other year and I might look different. I might be like 60 years old right now and be your teacher. Hopefully I'm not still using these videos when I'm 60. Sorry, moving on. Okay, so we are going to look at Unit 5, Section 2, which is understanding the complex number system and performing operations on complex numbers. So we are in your notes here, in your Unit 5 notes. We are skipping Section 5.1 and going straight to Section 5.2. Let's open this up and get it started. Here we go. Share the screen. Hopefully it focuses. Looks pretty darn focused to me. Okay, so I've got some of this kind of already done here because you don't need to watch me do all this. So there's a reason that we are talking about complex numbers right now, which is that this unit really is about quadratic functions and quadratic equations. And so it's kind of like, all right, quadratic chapter, why are we talking about complex numbers? Well, you will notice that sometimes when we solve a quadratic equation, the solutions come out as different kinds of numbers. And so we've got some examples of the different kinds of solutions that you can get to a quadratic equation. So we're kind of setting you up for this ahead of time before we really get into solving a lot of quadratic equations. We're just kind of saying ahead of time, hey, we're going to get different kinds of numbers as our solutions to these quadratic equations. So here's an example where I get real numbers are solutions, +3 and -3, and actually those are rational numbers. And remember that a rational number is just a real number that you can write as a fraction, just a over b, where a and b are integers. This symbol here, which looks like a C that's been turned into an E. That's a Greek letter epsilon, and it just means belongs to or is a member of something to that effect. So this means a and b are integers, b can't be 0, obviously. So a rational number is just any number that can be written as a fraction, is what that means. Sometimes you might solve a quadratic equation. You'll get an answer that is an irrational number. So like the square root of 12 is going to be an irrational number because 12 is not a perfect square. So if you type square root of 12 in your calculator, you're going to get one of those long irrational decimals that never repeats, never terminates, it never stops. Remember, we can simplify those rational numbers. Just an irrational number is a real number that's not rational. So in other words, the real numbers are made up of the rationals and the irrationals. Now, early on in the year, one of the first things that we did was to learn that there are numbers in the world that are not real numbers. And let's just remind ourselves of those numbers that we called complex. So if we start off by just looking at real, see that the reals are separated into the rationals and the irrationals. And inside of the rationals, we have these other sets. The counting numbers are the natural numbers, the wholes and the integers. Those all make up the rational numbers. And then we also have the irrational numbers, like pi. The rationals and the irrationals go together to make up the real numbers. And we also have these other numbers out here called imaginary numbers, and we've talked about what those are before. And we've also mentioned that if you take a real number and an imaginary number and add or subtract those, you get what we call a complex number. Okay. So in this case, we can see that like if you square a number, you're never going to get a negative, right? So how can you add that to 9 and make it smaller and get 5? Well, that's impossible, isn't it? If we do try to solve this, we'll see that we get a negative number underneath that square root. That's an issue, and that's what's going to cause us to get an imaginary number. Okay? So imaginary numbers have i's in them, and actually in this case, if I'll go ahead and simplify this just a bit further. When we do the square root of 4, we get 2. And when we do the square root of that negative, when we have a negative under the square root, that causes us to have an I. Square root of -1 is equal to I. And it says that down here. I is equal to the square root of -1. And that's called the imaginary unit. So if you square that, it would be like just getting rid of the square root. And so I squared would equal -1. So what we're going to do for the remainder of this section is really just learn how to do some operations with these complex numbers. Okay, we're not going to do any more in this section with solving quadratic equations. That's just kind of a way for us to say, hey, this is where this is going to come up later in this chapter. When we start solving these quadratic equations, we're going to get some of these imaginary or complex solutions. But we're going to take a step back here and just say, okay, let's just deal with these complex numbers and see how that works. And it's actually really easy for the most part. So here I just have some expressions that have i's in them. And guys, we're just going to treat these like I is a variable. In this case, it's not actually a variable. It represents the square root of -1. But as far as simplifying these expressions, we just simplify them as we would if we were considering I as a variable. So in this case, I'm adding, so I've got this 2 minus 5i. I can go ahead and distribute this 2. 2 times -3 is -6. 2 times -2i is -4i, and then just combine my like terms. So the 2 and the -6 can be added together, and that gives me a -4. Then I've got -5i and -4i, and that gives me -9i, and that's as far as I can go. I want you to make sure that whenever your answer is supposed to be a complex number, that you are writing your answer in one of these forms, in a plus bi form. They must be written in that form. So you can see -4 is like the A. The A is the real number part. And then you've got the I part, the imaginary part. So you've got a real part and you've got an imaginary part. The I always goes second. The real part goes first. The I goes second. I know it doesn't really matter which one goes first and which one goes second when we're just kind of simplifying variable expressions, but with complex numbers, that real number goes first, the imaginary number goes second. Okay, here I'm going to start with my 7 plus 2i, and now I'm just going to distribute this negative. So -1 times -2 is +2. -1 times -3i is +3i. And now let's just combine our like terms. 7 plus 2 is 9. 2i plus 3i is 5i. And that's as far as I can take it. And I've got my real plus imaginary form. Okay, for this next one, I'm going to start by distributing the 2. So 2 times 3 is 6. 2 times 4i is 8i. And then here I'm going to distribute this negative. -1 times 2 is -2. -1 times 3i is -3i. Combine our like terms. 6 minus 2 is 4. 8i minus 3i is 5i. Okay, there we go. On the next page, we just kind of, our operations become a little bit more challenging. Like in this case, we're going to multiply these complex numbers. I've got 2 minus I, that's a complex number. 3 plus 4i, that's a complex number. See, they're both in that a plus bi form, and we're going to multiply them. And guess what? You're just going to FOIL it. We're just going to use FOIL here. So 2 times 3 is 6. My outer product would be 2 times 4i, which is 8i. My inner product is -i times 3, which is -3i. And then last times last here is -i times 4i, which is -4i squared. And we're going to talk about that I squared in a second. But for now, let's just combine these I terms that we have here. So the 6 is good. We're going to let him stay just a 6. 8i minus 3i is 5i. Now let's deal with this -4i squared. We talked about this earlier, that if I is equal to the square root of -1, then if we square that, right, if we square this, the squaring would get rid of that square root. And so I squared really is just equal to -1. So this is -4 times I squared, which is the same as -4 times -1. Anytime you see an I squared, you're going to always want to replace that with a -1. We should never have any powers of I in our final answer. should never have I to an exponent, except for I to the first, obviously, okay? So -4 times -1 is +4, and then I can add 6 and 4, and my answer now is 10 plus 5i. Okay, we're going to FOIL here again, so -2 times 3 is -6. My outer product is -2 times 2i, which is -4i. My inner product is -2i times 3, which is -6i. And then last times last, -2i times +2i would be -4i squared. Well, we have that same kind of -4i squared there that we had last time. If I combine my like terms here, -4i minus 6i is -10i. And then just like last time, that -4i squared becomes +4, because it's -4 times -1. That I squared is -1. -6 plus 4 is -2. So I'm just combining my like terms, and there's my final answer. Okay, here I'm squaring this number, which really just means I'm multiplying 3 minus 2i times itself. So 3 minus 2i times 3 minus 2i. So I'm still just going to FOIL this. So I'm going to start with 3 times 3, which we know is 9. I'm going to do kind of 2 steps at once here. My outer product and my inner product are going to be the same. I'm going to have -6i here and -6i here. So that'll make up a -12i when I combine them. Now, -2i times -2i, negative times a negative is a positive, and that'll be 4i squared. Okay, this is plus 4i squared, whereas last time we had minus 4i squared. So let's be careful with that a little bit. So we're adding 4 times, and that I squared is really a -1. So this 4 times -1, that's a -4. So we've got 9 minus 4. This is 9 plus -4, which of course is 5, and then our minus 12i. There we go. Let's keep plugging along here, multiplying again. This time, we have what we remember to be a difference of squares, where the outer product and the inner product are going to cancel each other out. You'll notice that these two complex numbers are exactly the same, except one's a positive and one's a negative. Every time you have that situation, that outer and inner product are always going to cancel each other out, -3i and +3i. And so there's just no reason to do the O and the I step of the FOIL. So I'm just going to do first times first, 3 times 3, which is 9. Last times last, +i times -i is -i squared. So we start with 9, and we're subtracting I squared, which means we're subtracting -1. So this is really 9 plus 1, which is 10. You'll notice there that we just got 10, right? It's just a real number answer. You do not need to write 10 plus 0i. You don't need to do that. There's no reason to add plus 0i. That's just a waste of time. Let's move on to this next one. We still are going to FOIL here, and then in the last step, we'll multiply by the -3. So we're not going to worry about the -3 just yet. I'm going to go ahead and FOIL here. 2 times -2 is -4. I'm going to do my outer and my inner all at once. So my outer product is going to be -6i, and my inner product is going to be +2i. So I've got a -6 and a +2, which would be -4i. And then last times last, -i times -3i would be +3i squared. Okay, let's see what happens here with that +3i squared. That's going to be 3 times -1. Remember, the I squared is -1. So 3 times -1 is -3. So really, anytime you have an I squared on something, it just changes its sign. Let's combine our like terms inside this parentheses here. -4 and -3 is -7. And then I can distribute my -3. So -3 times -7 is +21. -3 times -4i is +12i. Again, always making sure to write the real number first. Let's move on and do number 9 here. This is just straightforward FOIL here. -3 times -1 is +3. My outer product is +6i. My inner product is +5i. So +6 and +5 gives me positive 11i. Now last times last is negative 5i times negative 2i, which is positive 10i squared. Now, like I said last time, anytime we see something times I squared, it's really just going to change its sign, right? 10i squared is just negative 10 because it's 10 times negative 1. And then 3 minus 10 is negative 7, so we have negative 7 plus 11i. All right, moving right along here. Now I've got 3 of them to multiply together. I'm going to leave the 2 plus I for last. I like to have that binomial in the front as the last thing that I do. And so I'm just going to multiply these second 2 numbers together. Let's see how this goes. So negative 1 times 4 is negative 4. Let's do the outer and the inner. So the outer is going to be negative 2i. The inner is negative 12i. Add those together, and we have negative 14i. Last times last is negative 3i times positive 2i. That's negative 6i squared. Okay, we're still not ready for the 2 plus I, so we'll leave that alone. Negative 6i squared becomes a positive 6. That's negative 6 times negative 1, which is positive 6. And so now, inside these parentheses, we can combine like terms. Negative 4 plus 6 is 2. So we have 2 minus 14i, and now we get to FOIL all over again. Here we go. 2 times, I'm going to switch colors now. So 2 times 2 is 4. We'll do our outer and inner. My outer product is going to be negative 28i. My inner product is positive 2i. Add those together, we get negative 26i. Last times last is a positive times a negative, so it's going to be negative 14i squared. Negative 14i squared simplifies as just plus 14. And then 4 plus 14 is 18, so we have 18 minus 26i. Okay, for number 11, we see another situation where the 2 binomials are exactly the same, except in one of them, the middle sign is a negative, and in the other one, the middle sign is a positive. We know that in those cases, the outer and the inner products are going to cancel each other out, so we don't need to do them at all. We'll just do first times first, which is 9, and last times last, which is minus 4i squared. And we know negative 4 times negative 1 is positive 4. 9 plus 4 is 13. Notice again that we just got another real number just like we did in number 7. It looks like every time we've got that difference of squares, that the I part just goes away, which it does. The outer and the inner cancel each other out, and there's no more imaginary part. Okay, we'll talk more about that later. Let's go on and finish number 12 here. So we're going to start by squaring 2 plus I. So that means first times first would be 2 times 2, which is 4. My outer and my inner would both be 2 plus 2 times I. So we'll have 2i plus 2i, which will be 4i. And then I times I will be I squared. Okay, now let's FOIL these 2 guys. So negative 2 times 3 is negative 6. My outer product is positive 4i. My inner product is negative 3i. Add those together, and I just get plus 1i. Last times last here, negative I times negative 2i would be plus 2i squared. Let's combine like terms a little bit here. I have a 4 and a negative 6 that adds up to negative 2. I have a 4i and a 1i, which adds up to 5i. And then I've got an I squared and a 2i squared, which adds up to 3i squared. Now we know that that 3i squared is 3 times negative 1, which is negative 3. And then negative 2 and negative 3 add up to negative 5. And so our final answer is negative 5 plus 5i. Okay, that was a lot of practice there just with complex numbers. At the bottom of the page here, it discusses that situation that we saw in exercises 7 and 11 where we had a difference of squares, meaning the two binomials were the same except for that center sign. Numbers like this, when they are complex numbers, are called conjugates. Those are called complex conjugates. And anytime you multiply a complex number by its conjugate, you'll always end up with a real number as your answer. So in number 7, these two numbers make up a difference of squares. So these two numbers, 3 plus I and 3 minus I, are considered complex conjugates. That means that when you multiply them together, your answer is a real number, meaning it doesn't have an imaginary part. Same with number 11. 3 minus 2i is a complex number. 3 plus 2i is a complex number. They make up a difference of squares. Therefore, these two complex numbers are called complex conjugates, meaning that when you multiply them together, your answer is a real number. Now, I go through and do a whole proof of that in the notes that I posted online, the completed version of the notes that are online if you want to go look at my proof. Okay, we have one more thing that we're going to learn in this section dealing with complex numbers, and that's how to divide complex numbers, because that seems like a tricky thing to do. How are we going to divide these things? And ladies and gentlemen, if you try to do 3 divided by 1 and then 2i divided by negative 3i, you have forgotten how division with fractions works. Please don't be that person. You can't just divide the real numbers and then divide the imaginary numbers. That's just not how division with fractions works. We'll discuss that more in class, but if you're watching this, you weren't in class, I'm just going to say, don't do it that way. Okay, so in order to divide complex numbers, we're going to have to make use of this idea of a complex conjugate. I'm going to show you how we do that here. So first of all, we can understand that this is not just an expression that we're simplifying. This is a division of two numbers. Okay, this is a quotient of two complex numbers. 3 is a complex number. Every real number is complex, and we are dividing that by 2 minus 2i. And of course, 2 minus 2i is also a complex number. So we are dividing two complex numbers. I'm going to recopy this here. We're just using this fraction bar to indicate the division. Now here's the way, and you'll see that it's going to get a little bit more complicated. Like first we start with a real number on top, and then we'll go to an imaginary number on top, and then we'll look at examples where we have full-on complex numbers in our numerators. But let's just start with a real number in our numerator. The way that we're going to go about doing this is by eliminating the irrational part of our denominator. Okay, we're going to eliminate the irrational part of our denominator. So we're going to kind of make our denominator a real number. Now think about what I just said. We're going to make our denominator a real number. Think about what we've learned about what you can do to a complex number to obtain a real number. Well, we just learned that if you multiply a complex number by its conjugate, you'll get an answer that's a real number. So that's exactly what we're going to do here. We have a complex number in our denominator. We're going to multiply that complex number by its conjugate. And that means that in the end, in our denominator, we'll have a real number, meaning no more I. To form the complex conjugate, we just change the negative into a positive. If this had happened to be a positive, then we would write this as a negative. We just change that sign. Now, the only way we can make this a legal move is if we also multiply by that quantity in the numerator of the fraction. If you have a fraction whose numerator and denominator are the same, then that fraction is effectively equal to 1. Anything divided by itself is 1. So I'm really multiplying this thing. I'm multiplying it by 1, by a fraction that's equivalent to 1. Now, let's see what happens when we do this. In our numerator, well, it's just 3 times 2 plus 2i. In the denominator, we've got 2 minus 2i times 2 plus 2i. This is a step that from now on I'm going to skip, but I think it helps to show it this time. So you can see that I'm just distributing this 3. So 3 times 2 gives me 6. 3 times 2i gives me 6i. In the denominator, 2 times 2 gives me 4. Now remember, I know that I've got a difference of squares here, so I don't need to worry about that outer and inner, the O and the I part of the FOIL, because I know they're going to add up to 0 anyways. So I've already done first times first. Now let's do last times last. Negative 2i times positive 2i is negative 4i squared. And let's just continue to simplify. 4 minus 4i squared, well, that's negative 4 times negative 1, which is really just plus 4. And now in my denominator, I have 4 plus 4, which is 8. Now this next step is one that we're going to go into a little bit more discussion about in class. I'm going to shorten it since this is a video. I want my final answer to be in that form, a plus bi. I'm not there yet. I need to have a real number plus an imaginary number. Now, the way I want you to think about this is that we are distributing the dividing by 8. Okay, we are distributing the division by 8, which means this 6 gets divided by the 8, and then we add, and then this 6i gets divided by the 8. I'm going to write it as 6/8i. So we have distributed that division. And now all we have to do is simplify our fractions. 6/8 is 3/4, and then this 6/8 is 3/4. And so our final answer is 3/4 plus 3/4i. Now if you want to ask, can I write this as 3i over 4? Yeah, you can, but I'd rather you didn't. I'd rather you write it as a coefficient times I, right? 3/4 times I, as opposed to 3i over 4. Let's go on to number 2 here. I'm just going to rewrite this so it's a little bit bigger. Our approach to this is going to be the same. We're dividing two complex numbers. We're going to do that by eliminating the irrational part of our denominator. And so we're going to multiply this denominator by its complex conjugate. The conjugate of 3 minus I is simply 3 plus I. It's that easy. If you multiply by 3 plus I on the bottom, we have to multiply by 3 plus I in the numerator. And now we just do it. Let's do it. 2i times 3 is 6i, and then 2i times I is 2i squared. In my denominator, the denominator is the easiest part. It's a difference of squares. Just first times first, last times last. 3 times 3 is 9. Negative I times positive I is negative I squared. Now you see this 2i squared? That's just going to be 2 times negative 1, which is minus 2. On the bottom, I'm subtracting I squared. So this is 9 minus negative 1. You see in the top here how I've got the imaginary part first and the real part second? That's not the way that we like to do things. We like to have the real number first and the imaginary number second. So I'm going to change that to negative 2 plus 6i. And then in my denominator, of course, I've got 9 plus 1, which is 10. And now I'm going to distribute this division again. So I'm going to divide the negative 2 by 10. And I'm going to divide the 6 by 10. And that'll be my coefficient of I. So that's negative 2/10 plus 6/10 I. Now we just reduce our fractions. Negative 2/10 is negative 1/5. 6/10 is 3/5. And there we have our a plus bi form. And that number, this complex number, is the quotient of 2i and 3 minus I. That's how it works. We've got 2 more examples here. We're just going to do the exact same thing. I'm going to rewrite these problems just because I think it helps. You don't have to. Okay, now in our numerator, we have a complex number that is a binomial. It's going to add a little bit more complexity, but not really. The basic idea is the same. We always multiply by the conjugate of the denominator. See, the idea is to end up with that real number like 10 or 8 in our denominator, so then we can distribute that division. So we're going to multiply by the conjugate of the denominator, which in this case would be -2 plus 3i. Notice that the negative on the 2 stays the same. It's only the I part that we change the sign of. We have to multiply by that in the numerator as well. And now let's just start multiplying. So we're going to have to actually FOIL in the numerator here. So 2 times -2 is -4. My outer product is 2 times 3i, that's 6i. The inner product is -2i, add those together, and we get 4i. Last times last is I times 3i, so that's 3i squared. My denominator, this is the easiest part, difference of squares, don't need to do the O and the I. First times first, last times last. -2 times -2 is +4. -3i times +3i is -9i squared. Okay, let's keep going here. -4 plus 4i. 3i squared is going to become a -3. On the bottom, I've got a 4, and then -9i squared is going to become a +9. -4 plus -3 is -7, and then we've got a +4i. In my denominator, 4 plus 9 is 13. There's that real number in the denominator that we were going for, and now we distribute the division. -7 divided by 13 is just -7/13, plus 4i divided by 13 is just 4/13i. Again, writing that as a coefficient times I. That's it. Last one. Okay, we're going to take the complex number 3 plus 2i, and we are going to divide that by the complex number 4 minus 2i. We're going to do this by multiplying by the conjugate of the denominator, which is 4 plus 2i. We just change the minus into a plus. We have to do that in our numerator as well. We'll need to FOIL in the numerator. So 3 times 4 is 12. My outer product is 6i. My inner product is 8i. Add those together. They add up to 14i. Last times last is 2i times 2i, which is 4i squared. In the denominator, don't have to do the outer and the inner because they cancel out. 4 times 4 is 16. -2i times +2i is -4i squared. In the numerator here, that 4i squared is going to become a -4. Right? That's really going to be a -4. So 12 plus -4 is 8. And then we have our plus 14i. In my denominator, this minus 4i squared is going to become a +4. So I have 16 plus 4, and that's 20. There's my real number in the denominator. Now I distribute that division. 8 divided by 20 is 8/20, plus 14i divided by 20 is 14/20 times I. Don't forget to reduce those fractions. 8/20, let's see, 4 goes into 8 twice, 4 goes into 25 times, that's 2/5. 14/20 is just going to reduce to 7/10. So 7/10 I, and there is our quotient. Hooray! We have finished section 5-2. Congratulations, we made it. I don't know how long that took us. Feels like it was a while, but we did it. Okay, so hope you're doing well. Look forward to seeing you again when you're at school. Goodbye.